No.
The point talk is from Fabian Bautista from
Yeah, thanks. So thanks a lot for coming, and thank you for the invitation. So this talk is gonna be, this history about higher spins. It's gonna have a little bit of overlap with the Justin talk from a couple of weeks ago, but hopefully we're gonna find also new elements. So it's based in a couple of papers that we wrote combining with the Alfredo Guevara, Christopher Nack, and Justin Vine. And then a paper that I wrote by myself this year about applying this to the two-variable problem. Okay, so applying this talk, be a little bit more for general public, so not necessarily expert in the topic. So I'm going to introduce some elements on the history about this higher spin stuff. And when we approach the two-variable problem for scattering amplitudes, and I have some original contribution from this work. But also, I want to underline the possible opportunities for new research avenues, connecting this two-variable problem, and especially opportunities in two-dimensional conformal. Okay, so I guess I don't need to motivate much. So in the scattering amplitude picture of the two-variable problem, we don't think of bounded system, but we'd rather think of a scattering system. Like for instance, we think of compact objects in an effective way. So we can model them like point particles with some structure, which you can introduce by introducing higher spin operators. And these point particles, they are gonna exchange gravitons between themselves, and we can radiate graviton as well, the gravitational radiation on Earth, right? So in this EFT description, which is a QFT description, you have to have a prescription to take the classical limit. And we have learned from several people how to do this. For instance, you can take the limit in which you have a large angular momentum or equivalent, small momentum being transferred between these two guys. If you have radiation, you're going to ask this radiation to have a wavelength much bigger than the size of the individual objects. And in general, if you have a spin, you're going to ask for this quantity A omega to be of order 1. That basically means, keeping all of this in expansion for these guys. So what is the advantage of thinking of the two-variable problem from the scattering amplitudes perspective is that we can exploit the power of unitarity and basically build, higher loop amplitudes starting from building blocks. And these building blocks, they are very nice because they satisfy, several properties we heard yesterday in JJ's talk. For instance, this object has very nice double complicated structure. And the idea of this talk is that we understand a little bit better those building blocks when we actually think of them as having anything to do with Kerr black hole. And okay, so we do scattering, and if you want to go to the bounded system, there are some prescriptions that work artificial perturbation theory to go from the boundary to the bounded system, as we heard about. We can also talk last week. So let us start with the simplest case. So instead of considering the two-way problem, they just consider one black hole. And basically, the simplest black hole you can think of is the Schwarzschild black holes. It's described by this metric, so you have a horizontal position 2GM. And if you take that metric, well, this metric has a dimensionless parameter, which is this ratio to the overall, it's a Teukolsky parameter. And if you expand that metric in powers of GM over R, you can do like this. And for instance, these form factors are real by delta functions, sometimes tensor structure that you sort of extract by expanding this metric. So from an amplitude point of view, it turns out that you can model this Schwarzschild black hole from a massive point particle spin 0, which is minimally coupled to gravity. So by that, what I mean is that you can compute these form factors from off-shell 3-point amplitudes, and people have actually realized that you can match these form factors to the ones that appear in this function of the function metric at the given ordering perturbation. So for instance, back in the 70s, Dove has to do this at 2 p.m. order, and this expansion has been expanded to 4 p.m. order already by Kerr algorithms. So the idea basically is that if you were able to do all orders in perturbation theory, you should be able to recover the horizon of the Schwarzschild. So, okay, so the next step would be to consider not a scalar black hole, but rotating black holes. And the simplest rotating black hole is the Kerr black hole. So this guy, and it has 2 horizons, which are the solution for this equation. And these 2 horizons are real so long as the spin parameter of the Kerr black hole is smaller or equal to 1. So in this problem, there are 2 dimensionless free parameters, as opposed to the Schwarzschild case. So there is a positive parameter, but there is also either the ratio of the ring singularity of Kerr divided by the position where we're measuring, or also you can find another parameter, which is a combination of these 2, which is the spin parameter of the Kerr black hole. So we can do the same as we did for the Schwarzschild black hole. So expand your metric in a post-Minkowskian expansion. You expand in powers epsilon. But then what we're going to do is that we are going to keep all of orders in the spin multiple expansion, so all orders in the R. So when you do that, that is equivalent to deleting the horizon of the black hole and then basically with a naked singularity of radius A. And the linearized metric for that case, as we have learned from Justin, has this very nice exponential structure. So it's like a chip acting in the Newtonian potential, which is known as the chip. The nice connection to the scattering amplitude story is that perhaps in this paper by a couple of papers by Guevara, Jerome White, and between one of collaborators, in which they realized that if you compute the 3-level scattering amplitude for a mass particle of infinite spin, which is emitting a graviton, this amplitude has a very similar exponential structure. And it turns out that if you use this amplitude as a source in the right-hand side of the Einstein's equation, what you will recover is the linearized version of the Kerr metric. So, but then from an amplitude description, you start to make some sense of this sign that appear in the Kerr metric, the helicity of the graviton here. So this amplitude, in fact, is very constrained and is unique. So doesn't have any freedom, and the only requirement that you ask for this amplitude is that the massive particle here is minimally coupled to gravity. So minimal coupling means basically that if you take the massless limit of this guy, you recover the massless amplitude, and this massless amplitude is fully constrained by Lorentz arguments. So there is a sort of formal story of how to strike the classical spin parameter of Kerr black hole from the Fabian Bautista operator, which we can do introducing spin coherent states, but for the sake of this problem, we're just going to assume that it's this exponential that gives you the classical linearized metric. I also wanted to point out this recent paper by Lucille, Kangemi, and Paolo Piccinci, in which instead of starting from IPhT amplitude, they start from string theory amplitude. Taking the classical limit of leading Rayleigh string amplitudes, they are able to extract like classical triple amplitude that look kind of similar to this guy. It's like an exponential, the fourth order in the in multiple expansion, but then beyond order the fourth, this amplitude started to seem like some string contribution. So it's not exactly the Kerr amplitude, but it looks very similar. And probably we're going to be hearing a little bit more about this in Gabriel's talk first.
So you get alpha prime correction? Is that what you're talking about?
Well, it turns out to be, an amplitude which doesn't describe this rotating guy, but sort of like a classical rotating string.
The string just gives you alpha prime correction. So you can new parameter. Is that what you're saying? Correct?
No, it turns out that you can just write the classical computations. Imagine just a classical rotating string. And then those sort of classical stringing contribution start to show up at order 8 to the 4. So that's what they match with the update starting from string theory.
Yeah, I guess when you say stringy, you mean alpha prime. I mean, when alpha prime goes to 0, those stringy can go away.
They should go away.
And does anything sick happen? I mean, because the ASR is much greater than 1. Are there any diseases coming because your solution is not real?
Well, there are some subtleties in this sort of continuation which appear, and we're going to be talking about this in the dynamical case. But basically, if you do this, you're basically deleting the horizon of the black hole. Many of the physical processes that happen at the horizon, you're going to start with the weird and the black hole.
It's more than just horizon. The solution is not physical.
Yeah.
So is something sick happening, or is there a problem with the amplitudes, or you say it's just some unitary thing?
No, it's just an amplitude that doesn't describe an actual black hole. It describes a native singularity. That's it. It cannot be a physical object, but still it's like some mathematical object. Okay, so we can then perturb black holes. There are two ways of perturbing black holes. So one is either putting a companion for this black hole, like for instance, we have heard from Oleg's talk how to put this in string Mar ratio case, and approaching this problem from self-force computation. There's another way of perturbing the black hole is by throwing a massless wave, like plane wave. So this plane wave is going to be basically scattered because of the gravitational rotation created by the black hole. We're going to see that these processes are actually very related, and we're going to study them individually. So let's start with the perturbation by a second body, and the idea of the scattering amplitude basically is to compute observables in two bodies. So for instance, you can scatter two black holes with say aligned spin being aligned in the direction of the angular momentum, and compute observable like the scattering angle in perturbation theory. In the P expansion, we compute this guy ordered by order G over B. So people have done this in a lot of simple, well, not simple, but the Schwarzschild case scenario results very like 40, and now in the spin case there are results of lower orders in perturbation theory, and the leading the leading order in the Cosmic-Oscar expansion was computed by gluing these two triple amplitudes into exponential, and it turned out to show perfect agreement with the ER computation that we do. So Even though these are lean order in GM over B, they keep all orders in the spin multiple expansion. So the next step would be to say, okay, how about if you put, instead of putting just 2 3-point amplitudes together, you put 2 3-point amplitudes and analogous amplitude with an additional graviton here. So it's like a quantum amplitude. And this amplitude is known from the literature, from the Cunningham 101 amplitude. And in the paper by Guevara Vine, they put it here and have the conjecture what the scattering angle 2 p.m. for the scattering of black hole of 4th order spin may look like. So it's a conjecture that a scattering angle that doesn't have any free parameters. So there are also some other results for the generic spin orientation by Euthenian collaborators, again using the Cunningham 101 amplitude, but allow the spin to be oriented in generic direction. There are some even beyond spin to the 4 conjectures by Bern and collaborator and Outlet on the stuff in this paper. We have heard of a result up to 3 p.m. Quadratic order spin last week, and there are a couple of papers that appeared last week, 3 p.m. including spin orbit correction to the scattering angle. So all of this has been derived within the context of minimal coupling amplitudes, and these scattering angles do not have any free parameter, and in principle, you may ask whether these have actually anything to do with Kerr Binary. So the only guidance that people had for writing those amplitudes is that this 3-point amplitude is the exponential of Kerr, but other than that, they didn't have any other guidance that tell you that this is actually Kerr Binary. So back in 2019, Justin and Niels tried to make some connection between the GOV prediction for the scattering angle and actual computation in gravity. So computation within the gravitational self-plots. And well, there was still some work to be done here, right? So the main input for this right-hand side are these exponentials. So the 3-point amplitude that we discussed, and then there's also a Cunningham 101 exponential, which is, as many of you know, is valid up to 4th order in the expansion of this exponential, because you start getting spurious spot contributions to this expansion at 5th order spin. So what at spin to the 4th is something that should define. So you have to find a way of comparing the prediction from these two kind of computations. So this was a computation done for black holes with a line spin going circular equatorial orbits. And there are analytic results for these guys for observables like the redshift or the precession frequency at very high orders in the PN expansion. So definitely be able to compare to the scattering angle prediction. So the way of doing it is by mapping the problem to one of the two sides. So the way in which Justin and Niels did it was by mapping the scattering problem to the bounded problem through a Hamiltonian that you can compute from the scattering angle and then from the equation of motion and the first law of black hole mechanics by Euthenian collaborator. You can compute the observables, the inverse redshift of the precession frequency, and then you can compare to what you have in the GR computation. So what were the findings from Justin and Niels was that if you take the result from your quantum amplitude and you expand it to the 3rd order in the spin multiple expansion, there is perfect agreement between the quantum predictions and the black hole perturbation theory computation. However, at spin to the 4, they found that there is still some room for correcting this quantum amplitude. So in particular, you're going to start introducing contact operators in this amplitude at 4th order in the spin. And in particular, at 4th order, you can have 3 operators. And the matching to the self-force computation can give you only 2 relations to solve for these 3 coefficients. So this aligned spin scenario cannot tell you fully, what is the quantum magnitude for that spin. One way of finding an additional constraint comes, for instance, by requiring that your quantum amplitude is symmetric if you shift the spin of the black hole by a amount proportional to the transfer momenta. So we know that this exponential is invariant if you shift A by that. This guy is also invariant because W is basically made of the spinors of these two guys. Once you shift it by this guy, this remains invariant. But these other couple of terms, they are not invariant. So if you want to ask your amplitude to be invariant and the shift symmetry, you can kill these two coefficients, and by this relation, kill the other one. Especially that basically the shift symmetry quantum amplitude is at spin to the 4 is this exponential.
Sorry, I'm not with you. What does it mean you want to impose it? Or is
no, you don't want to. You don't want to. In general,
how does symmetry or is symmetry?
No, it was proposed. Sorry, I didn't tell it. So it was proposed that it was proposed in the context of the two-body scattering amplitude that the observables of the fourth order in the spin multiple expansion, they should have that symmetry.
I don't know what it means it was proposed.
It was an observation. It was an observation that,
It's not a theory that you can check if it has a symmetry. I don't understand it. I'm sorry, I'm listening to the point.
Okay, so
calculation or is it a guess?
It came out from the calculation and it was observed that up to the fourth order in the spin multiple expansion, this symmetry was satisfied.
But there's no theory that tells you if the theory is symmetric.
No. It was just an observation. And people proposed maybe this is the symmetry that should guide you the computation of observable to higher orders in the spin multiple expansion. And we're going to come to that in a moment. So it was just an observation, and I'm just saying that if you were to impose that symmetry, you could fully fix the quantum, but in general, you don't have to, right? You have to compare, like this has to come out from the computation instead of imposing. But anyway, so let's imagine that you allow for these extra coefficients in your quantum, and you will ask, how does the scattering angle gets shifted from these coefficients? So it turns out that if you go to the high energy limit, meaning basically the limit with which the velocity of these guys goes to 1, this scattering angle is divergent. So you may also impose, that you want to get observables well behaved in the high energy limit and obtain another constraint that allows you to kill all of them. So, but in general, you don't have to. We are saying this has to come up with the theory. But something that one learned from studying these two simple scenarios into the fourth theory is that shift symmetric amplitude implies a smooth high energy limit for the observable, for the two-body observable, but in general, the opposite is not true. It is true in this case, but if you go to higher orders in multiple expansion, it doesn't have to be the same. So okay, the self-force computation tells us that you have just these two relations, and you need basically additional data from the self-force computation to be able to tell that these two coefficients are 0. And this could perhaps be done if you have a self-force solved for orbits, and there is a very nice paper that appeared this year, but it still need to be proved in this two-body context. There's something even more critical that you can do for deforming the quantum amplitude of fourth order spin already, which is enlarging the basis of a spin. So before the spin parameter of the black hole had 3 degrees of freedom, you can introduce an additional degrees of freedom by allowing this mod 8 operator. And the mod 8 operator, you can write a context information at spin to the 4th here. It turns out that the aligned spin scattering angle doesn't see that context information. So in order to see it, you have to do computation from misaligned spin. And that means basically restoring back the absorptive, the dissipative contributions in the self-force computations, which we don't have at all. So Message basically is that there is still a lot of room for correcting this amplitude, even at fourth order speed, and you need a way, a clean way, to tell what are the values for these coefficients. So we are going to find the way of fixing all of those coefficients at fourth order speed, but also going to higher order systems. So the way of doing it is basically about removing the other body, and instead of considering the second body perturbation, we are going to consider a wave perturbation of Kerr black hole, and one should be able to relate that to the complex amplitude that we have been talking about in the low energy limit and the super extrema limit, as is the case for the linearized metric. So what we want to compute basically is the differential cross section for this scattering process happen, which is given by the the flux of the outward energy flux for the scatter wave normalized to the energy permittivity area of the incoming plane wave. And so you're gonna split this contribution in general for generic helicity of the or spin of the perturbation. So S and H here. So you can have in general two contributions, so one for the helicity conserving amplitude and one for the helicity reversing amplitude. So this guy in general is zero, or it's not zero only for spin two perturbations. And the way of finding this these two contributions by solving the Teukolsky equation. So the Teukolsky equation basically tells you that this couple of amplitudes, you can write them as this sum of spin-weighted spheroidal harmonics times a factor which is a phase shift. And this phase shift you can fully solve by solving the radial Teukolsky equation. So
in the Teukolsky equation, how do you see two contribution on the risk preserving, risk reserve, and reversing?
Well, they are just defined by this way, right? So one is the sum, and the other one is this other sum of parity. The parity. Well, with this factor of minimum.
Yeah,
no, Teukolsky just tell you what is the phase shift.
So the phase is delta LMP. Is it the same for parity percent?
Yeah. This guy comes just from solving the radial Teukolsky equation.
And is
the other is just doing an analysis of waves propagating in this class.
So the delta is the same for F and G.
Yes, the delta. But of course, the full amplitude is different just because there. Okay, so this is actually a not very straightforward problem. And in general, finding an analytically closed solution for this equation is still an open problem. And the reason is that the Teukolsky equation is actually a very interesting equation called the point equation. So in general, well, let me just tell you a little bit about the Hoynes equation. So it's a second order differential equation with 4 singular points. So 0, 1 at z equals 1 at some point A, and then another singular irregular singularity at z equals infinity. And this you can think more or less as a generalization of the hypergeometric function. You can, by that I mean that you can obtain the hypergeometric function certain in the expression up. So for the case of a gravitational wave scattering of a Kerr black hole, the radial Teukolsky equation is not the full Hoynes equation, it's a special equation, which is called the Hoynes equation. It's an equation with the 3 singular points instead of 4, one at z equals 0, z equals 1, and z equals infinity. And it turns out that actually any perturbation of type D metric can in general be able to be written as some kind of integration. So as I'm saying, like finding closed solution for this equation is still an open problem. There are some formal solutions, and we're gonna review them now. because actually these kind of equations have appeared a lot in the literature, not in the sort of amplitudes approach, but it appears a lot when people are doing scattering theory of the four-dimensional patterns. For instance, it appears when we are doing computations in quantum field theory in curved space-time, and in those scenarios, what people are interested to do, for instance, is computing the point amplitude to these backgrounds, which is going to provide for you quasi-normal modes, great value factor, log number, Hawking radiation, etc. So, for instance, there's this very nice formula from universality that arises from the low energy absorption cross section, which is basically given by the area of the black hole, independent one activation from the black hole. But so I want to underline two possible connections of this scattering amplitude to this literature of scattering theory of Kerr black holes. So one of them is given by studying the monodromy of this scattering problem. So basically, you're going to extract scattering data from studying the singularity of your equation. So it was a very nice paper by Alejandra and some collaborators. And it turns out that you can compute this monodromy coefficient from some CFT techniques, which I'm not very familiar with, but and in this case, it's in the limit of the central charge for one. The second connection is, let's just forget for a moment about this Points equation and Teukolsky equation, just in the dimension CFT, and some multivertex operators in your CFT theory. So if you compute the level 2 null state equation from those operators in the CFT and take the limit in which the central charge goes to infinity, you recover a Schrodinger-like equation with regular singularities. And you can introduce a regular singularity from descendant operators, and it turns out that you can recover the whole entire equation, which you can then map to the Teukolsky equation. So you can map sort of the CFT parameter to the Teukolsky parameter. By doing this, there's actually a very nice paper that appeared that gives you analytic form for the quasi-normal mode quantization of the charge in black hole. And they are still written as a partition function for me equals to supersymmetric theory with 3 hypermultiplets. It is an expansion in some instant zone parameter, which roughly speaking is equivalent to this expansion to the cosmic constant parameter.
I thought it was for ABS, short ABS black holes.
Well, there are so this one that I'm talking about it has the quantization condition for exactly charge black holes. Okay. And there is a recent papers in which people have started applying this for Kerr black holes. So yeah, it has appeared in different contexts in ABS too. And basically what I wanted to emphasize with this slide is that even though we are not very well, at least I am not very familiar with this computation, there could be avenues for exploring this quantum equation. In this talk, we are not going to follow any of these CFT techniques. We're going to follow the usual, GR approach for solving the Teukolsky equation, which is based on this MST method for solving Teukolsky. So let us go back to that, to solving our radial Teukolsky equation, because we want to start this scattering amplitudes. So the MST method basically assumes that you can expand the solution for the radial equation in terms of some Coulomb functions that converge at infinity and some hypergeometric functions that converge at 0. And then you can join the two solutions. So by joining the two solutions, you will encounter some coefficient that satisfies the three-term recursion relation, which you have to solve order by order in perturbation. Once you solve for them, you cannot solve for this parameter, which is some renormalized angular momentum. So you can impose some boundary conditions, and the boundary condition that we can impose, for instance, are that the waves you have purely incoming waves at the horizon, and at infinity you have the superposition of an outgoing wave. And once you know that, then you can determine the phase shift, which is going to be basically given by this ratio of these two coefficients. So if you know these coefficients, you have solved the problem completely. So of course, this is not simple to do it because in general, this ratio of coefficients is a function of some gamma functions in there. But what I want to stress is that it's also a function of this AN coefficient that you have to solve with some partial relation. So these are infinite sums, very difficult to do. Like people haven't found ways of doing them. But fortunately, if you do a low energy expansion of your coefficient, then you find out that this sum actually truncates.
But those infinite sums, do they simplify in the Schwarzschild case? Where is the spin? Sorry, I don't see the spin.
Yeah, so the spin enters here through, say, nu, which is a renormalized angular momentum, which receives contribution epsilon, so spin enters through nu. It also enters through this a new coefficient, so these are very complicated coefficients.
But I mean, do they become more manageable with the Schwarzschild?
Yeah. I mean, in Schwarzschild, your equation reduces the rate Wheeler. So,
yeah, no, but I mean the ratio of the coefficient. I mean, if that ratio becomes some simple analytic.
yeah, actually.
Well, we can talk about it.
Well, what happens in Schwarzschild, for instance, is that in some cases you have to learn these sums. But yeah, it becomes a question. So, okay, so the strategy basically for us is, instead of trying to solve the full problem, we solve the problem perturbatively, expanding in epsilon parameter. But something important is that for this black hole perturbation theory methods to call, we have to keep the spin of the black hole smaller to GM, smaller than GM. And but then we want to compare this to the naked singularity scenario. So we have, after that, we have found the solution. We will analytically continue in the limit in which this guides, which is where we started from comparing with this triple alpha. Okay, let's say that you were able to solve for these coefficients in the low energy limit. You still have to find, you still have to do this infinite sum of harmonics. And in general, doing this infinite sum of harmonics can become very cumbersome. So what you can do is to go to a better basis. Instead of writing the spin weighted spherical harmonic, write them in terms of spin weighted spherical harmonics. And in this case, I'm talking explicitly about the spin 2 perturbations. So you're going to expand your modes or your scattering amplitudes in terms of powers of epsilon times some functions, what functions of the spin of the black hole and gamma, which is the angle formed by the incoming wave and the direction of the spin. So some saying like these sums are very difficult to do, and a better approach for us is to try to write an ansatz of what this GFT, what this amplitude might look like using GFT inputs, and then expand the ansatz on the same basis and compare to the black hole perturbation theory's solution more finally.
Yeah, what guarantees you that it makes sense the black hole perturbation theory in the large A limit?
It doesn't, it's just an extension. So, okay, so what does amplitude look like from a QFT setup? Well, as I told you, there are two helicity scenarios, the helicity preserving and the helicity reversing scenario. So for the helicity reversing scenario, there is a the Arcanic Hammett one-on-one form of the amplitude has this very nice exponential structure. And it turns out that this exponential is just enough to capture the Teukolsky solution in the super extremal ring. So actually, we checked that up to spin to the 6, at least, the black hole perturbation theory solution just reduces to this simple exponential.
And do you expect that to continue to higher speed for the
Well, it's hard to tell because even though you know it seems to be simple, some things could happen like the appearance of absorption that could also damage this very nice exponential behavior. So it's very difficult to tell what is the case. So okay, so that's for the helicity reversing amplitude. So that's very nice exponential. But then the more interesting case is the one for the helicity reverse preserving amplitude. So we have seen before that we have this exponential, and this exponential we said that it gets sick if you expand it at fifth order speed because you start to have contribution from this spurious. So our answer for this amplitude better correct those spurious poles. And we are going to basically propose an answer of this form, so you can factor out the helicity weights in the scalar amplitude. We're going to keep that exponential, but then we're going to add a function with some, which is going to be a function of the spin operator, but we shall correct the spurious pole, but we can also have full coefficients. So for writing that answer, we're going to use some physical constraints like neutrality, locality, cross symmetry, frequent factorization. And that gives you enough constraint to write this function as an expansion of three polynomials. And here I'm showing like the explicit form of this polynomial, the sixth order in spin. So it has contribution from these sort of operators in red. But I also say that you can enlarge the basis of a spin by allowing these mod 8 operators there. And this mod 8 operator turns out to have a very interesting role in the matching to the black hole perturbation theory computation because they capture absorptive effects at the horizon. So, okay, with the answers at hand, you can just expand it in modes and compare mode by mode to the black hole perturbation theory computation. And this is what you get from matching. So up to the fourth order spin, the comparison to the black hole perturbation theory computation tells you that all of the contact deformations up to the fourth order spin, they have to be zero. So by comparing to the self-force computation, we still have some room, but this problem allows us to match and fix them exactly to zero. So you can find result at fifth and sixth order spin, and these are given by these numbers. So this alpha parameter here, it captures, up to spin to the fourth, the black hole perturbation theory solution, they are just polynomials, whereas that spin to the five, you start finding non-rational functions. And this alpha parameter tracks the contribution from these non-rational functions. And it also tracks the contribution from the imaginary part of those rational functions. So these guys will capture absorptive effects at the horizon, and the other guys will capture. Something that you see is that once you put the value of this coefficient in your answer, the shift symmetry the symmetry that holds for this exponential by shifting the spin by this amount is broken. So, and in general, as we were saying, this was a symmetry that was proposed just by observation, but it's just not there from the Teukolsky computation. So if you analyze your answers before the analytic continuation, if you in general allow for imaginary coefficients, parity, your amplitude is parity even, but after analytic continuation, your amplitude is parity odd, basically because it is just a consequence of this analytic continuation. So the question is like, can you find say like a parity even contribution that can recover that can capture this sort of effect? It probably has to do within the framework of the recent paper by by Ali Socio and Rafael Aude, in which they analyze absorption by allowing the mass and spin of the outgoing particle to change. So in this case, we are writing an answer for this quantum amplitude with the mass and spin of the outgoing guy to not to change. So somehow the absorptive effects are captured. Yeah, the fact that the mass and the spin of the black hole has changed because of absorption are captured by these coefficients.
So questions, I guess, is left over from this and stuff. But AMU has how many independent coefficients? Yes. Components. AMU has how many independent components?
AMU has 3 independent components. If 3 independent components in a conservative scenario.
So it has 4. I just want the answers, is it 3 or 4?
If absorption, if it's absorbed, there are 4 independent.
So this computation is 4.
The additional degree of freedom is captured by this more data. So yeah, 4 degrees.
No, I mean, still just has 3 independent components. Your 4 things that you can write down are just different functions.
No, but they are independent. I mean, one is the mod, which is the square root of the other one. So they are not linear independent. So you cannot write the 3 components.
This is 3 components. Like one of those is a function of the other 3.
I mean, okay, it's 3 component if you pass the change in the mass and the spin in a different. I'm just saying that this additional degree of freedom that we are putting in there it should account for the change in mass and spin of the black hole once absorption has happened.
So there are no new 3 parameters as eta and alpha that show up with.
No, this is just a number. It's 1. I'm just putting there to keep track of what are the non-rational contributions and what are the real non-rational contribution and what are the imaginary non-rational.
And eta likewise is fixed to be some 1.
Yeah. Okay, so in that way, you can extract a quantum amplitude from black hole perturbation theory solution. So this is possible answer for what this quantum amplitude may look like in the super extremal range. So let me before going to using this quantum amplitude in the two-body problem, some applications of this quantum amplitude. So one of them is that, you know, in general, if you set unpolarized beam, say unpolarized gravitational wave, then you scatter of the black hole, the different helicity components will scatter by different angles. And you can measure what this polarization may look like, and actually back in 2015, there was a prediction of what this polarization may look like for a small scattering angle. So the prediction was basically based on the computation of this base input diagram from a, you know, massive particle of spin 1 exchanging a graviton with the massless polarization occurs. And the 0, 1, 2, 1/2. And the prediction was that this polarization should be proportional to the mode of the polarization. But it turns out that gravity is somehow special. So if you did the black hole perturbation theory computation of this, instead of finding a 2, you find a 1. So there is a discrepancy between this sort of graviton exchange diagram and what you get after perturbation theory. And it turns out that this discrepancy can be solved if you include the additional 2 diagrams that you quantum amplitude. So if you redid this computation that Barbieri and Guarantini did for the spin 2, for the helicity 2 scenario, you find that this 2 becomes actually 1 that is perturbation theories.
So however, Donald was missing what?
No, Donald was not missing something.
Okay.
Donald was the result that comes from black hole perturbation theory. What was missing something was the prediction from Barbieri and Guarantini. So they were missing this couple of diagrams. So their answer was not only not gauge invariant. So the gauge invariant can be restored by adding these two additional diagrams. But adding these two additional diagrams has very nice interpretations. There is a source. So naively, you expect that you're putting your background, and then this background is static. So you should expect the scattering amplitude to give you just by this gravitational exchange diagram. But somehow there is a sort that is responding to this perturbation, this sort, and this response is captured. A second thing that comes out from the computation is some universality in the large angular momentum thing. So if you take your black hole, you perturb it, and then take the limit in which the angular momentum of these partial waves is very big, turns out that the black hole doesn't care where you have thrown scalar wave, a gravitational wave, a neutrino wave. You get a universal result. And you can get a universal result to all orders of speed multiple expansion. So, but you know that comes basically from the study geodesic, large geodesic Kerr backgrounds, for instance. You could set to 0 the speed of the black hole, you just recover the usual universality of the Newtonian potential. So there is something interesting if you did the computation for massive geodesics, and it was actually done in this very recent paper by collaborators. So if you do massive geodesic computation and then take the massless limit, it turns out that the answer agrees with the black hole with the massless scattering only in the economy. So the message basically is that the massless scattering has more information than the massive scattering. So you cannot just get massive scattering from taking the massive scattering. Something that you can do with your partial waves as well is, compute what the scattering function for the massless scattering look like in this iconal regime, and as you would expect, the result that you get from the shift computation agree with the massless plotting massive scattering, which was at the RME with comparison with Vecchia and collaborators. There's also another way of seeing this universality when using Darwin-Kekin methods. This is a very solid result. So in the last 5 minutes or so, let me now move to an application of this quantum amplitude that we started from black hole perturbation theory solution to the 2-5 problem. So we're going to review the leading singularity computation that Guevara Ochinovai did in the line spin scenario, but now we're going to allow for these guys to have spin oriented in generic direction. So in here, we're going to put the amplitude that we started from black hole perturbation theory, so the company that we started from there. And here, we're going to have the two 3-point amplitudes. So I want to emphasize that this is a contribution on the super extrema region, the limit in which the horizon is. So basically, to obtain the amplitude, you just have to solve these complex integrals for one complex variable, so you can parameterize the kinematics in the problem in terms of that complex variable, and then just computing this leading singularity just reduce to a very simple residue evaluation. So you can organize your answer in terms of some spin operators. So for instance, this epsilon, which is contractions of the Levi-Civita with the momentum of the two guys, and the momentum transfer, and the spin of the other guy. You can have contractions of Q with S, contraction of the P of the Y, so the left hand side with the S of the other side. But there's also these mod N operators that I was telling you about that capture these sorts of. So in general, you can organize your 2-point amplitude in different powers of these operators, and the leading singularity computation should tend to basically about what are the coefficients in this way of organizing the amplitude. So you can do it up to 4th order spin very easily and recover all known results. But up to the 5th order spin, your result, as you have said, is chip symmetry. And it's broken basically by the contribution of some operators in your quantum amplitude, which not only have produced an amplitude which is not chip symmetric, it also produces an amplitude which gives you observable charging in the high energy. So for instance, if you went to a line spin scenario and ask, what is the high energy limit for the scattering angle, you find that that limit you have, if you plug the Teukolsky solution for this function, you find the number which is now d squared minus 1. This one is 0. If you plug the chip symmetric solution from Bern et al., you get a well-defined high energy angle because these K1 and K2 functions are 0. So you can use this amplitude and compute observable for the direct spin orientation using, for instance, this iconal formula that Bern and collaborator wrote. So you just have to take some derivatives of your iconal formula, which is just taking this amplitude and doing a two-dimensional Fourier transform. So then you can have a prediction of what the impulse and distinctive look like for transportation. They still have to be checked against some related words like capturing absorption by Saclay. So in conclusion, so we have shown a prescription of how to extract higher spin amplitudes in black hole perturbation theory solutions in the super extremal regions. We have used it in the two-body problem to make prediction of what the impulse and the spin will look like for higher orders of spin. At spin to the 5 unknown, this proposed symmetry by Bern et al. That the observer actually enjoyed, it's broken. And but something very interesting that is to study is this high energy behavior of these Teukolsky solutions for the observer. The future, which is something we are working on now, is how do you match a quantum amplitude without the need of going to this physical region? Can you restore the symmetry of Kerr, or does any other symmetry arise in that scenario? There is a very interesting of the double copy for the up to spin to the 4, which is just this exponential. Looks the same if you are doing the quantum, you're computing the quantum scattering electromagnetism. And the question is, does the double copy hold for higher orders of spin? So for that, you will have to do perturbation of Kerr-Neumann black hole, and then take the limit in which basically turn off gravity and keep the case. So that's something that you can work in the future. And also, as I was telling you, there is this CFT tools that people are using to approach similar problems in different Kerr backgrounds. Can help us study this session, start our story. So that's questions?
I've already asked, but what's the justification for extending the solution, saying that will continue the perturbation in higher speeds? Is it just a guess, or is
Sorry, say it again.
So you have a conjecture, I think, or prescription.
Yes.
We're starting with some regime where you know how to do perturbation and extending to another regime where there's some analytic continuation. If I understand correctly.
What you don't use.
So analytic continuation means you're assuming that nothing funny happens, right?
Yeah. Yeah,
what's the justification?
I mean, you expect that if you continue, you recover this naked singularity object, but in principle, funny things could happen in this.
So it's just a hope.
Exactly. But there is still some room, especially in the choice of boundary conditions, which we're still studying. That's why also
Exploration.
Okay.
But in the end, if solutions, then there are more. So this can be in the end, from there, solutions for real habits.
I mean, you can extract amplitude from there, but do they describe physical object? That's another question. And actually, what we want to approach now is the same, not having the need to extend this to the super extremal region, because in the end, you want to make predictions for actual black holes seen in the sky.
So something about my is you're computing, this diagram of post-Teukolsky and post-Newtonian. So you're computing now conditions in the spin direction?
Yeah, so there is an additional direction. So we fix the order in the post-Teukolsky expansion, which in our case is 2pm, just the triangle. But we are going higher orders in the spin multiple expansion. So known results up to spin to the 4 works really well. There is not any problem with the analytic continuation to the unphysical region. At the 5th order in the spin multipolar expansion, you start to find problems. We have some prediction what the result might look, but there's still some starting problems.
So at some point you showed a result of prediction from Barbier and others for the polarization and compared it with what we looked from like tradition theory, and you said there is an interpretation of adding those two less diagrams as if there's something reacting. How can we make this?
Well, you can see it from the diagrams, right? So in this case, the massive guide is just sitting there. Yeah. In this case, the massive guide absorbs the perturbation and then propagates the emits.
So I believe there's something I don't understand about the calculation of those items, because if I understand correctly, there's no propagator there.
There is propagator here.
Is there a propagator?
Yeah, of course.
Is one take the limit where the mass is?
No, there is a massive propagator.
This is done using two elements.
Yeah, there is different ways in which you can compute this amplitude, either from a Kami-Hammer amplitude. You can just take a spin 1/2 particle minimal coupling to gravity. So the spin 1/2 will give you the dipolar operators. Computation that you're making.
But that's way different from the where the mass is.
Yeah.
Okay.
Well, we do take the classical limit, sorry.
No, but even in the classical limit, there is a two-point function there. That's, for instance, if you span multiple, there is a two-point function with one. And even in the classical limit, you manifest on zero. Otherwise, you kill absorption.
I wouldn't say it's zero, but it would be a product of two.
It's not a problem.
It's not a product of two amplitudes?
No.
Basically,
what happens there is really at the core of the dynamics of your mass particle or your horizon level.
Yes. So
you do make this tracking of the amplitude. So first question is, how do you check that the amplitude you get is correct? And the second is because you actually extracted from something else in some regime, as we're saying, you need some analytic combination for hypergeometric functions in there. This is going to be very tricky. So the question is it the final word that the shift symmetry is going to be? It's not going to be present for spin.
well, what I can tell you is that it's broken for a super extremal guide. For an actual Kerr, I don't know. And I don't understand what you mean by checking that the amplitude is correct. I don't know. It's just the amplitude that comes up from doing the computation. You can write an effective Hamiltonian and write derive well, the way in which we wrote our answer was directly by writing an amplitude, but you can write an answer for a Hamiltonian and then write an amplitude and compare that to black hole equation theory solution. So in that sense, it is an amplitude. If you ignore this mod 8, guys, so it satisfies all the properties of an amplitude. It's say like there are point particles from which you can derive this amplitude. Does it describe black holes? That's a different story. But I don't understand what you mean by checking that the amplitude is correct. Well, there is other ways. Well, there is other ways of checking that you did the computation correctly. Like for instance, solving the self-force result, which is the two values of the problem. And for instance, we have checked that spin to the 4 is just the same. Higher order spin, we have still checked from this other self-force.
So presumably you can compute something like the scattering angle in this super extreme limit, and then analytically continue that as a function A. And is enough known about the
I don't think
it's been
I don't think probably for the conservative contributions you might do that, but the problem is really that at this order there is absorption.
Right.
And it's just difficult to think how to continue practice contribution.
Because of the absolute value.
Exactly.
Well, unfortunately, there are no analytic self-force results for scattering. Only for power. Also, then like much restricted, like a line span and even circular orbits, like the paper reveals.
And
Only in circular orbits.
well, I'm thinking of different kind of horizon, like say like numerical. Is that possible, or is that too?
This is way too deep and high orders. Things to hope to extract these kind of coefficients out of the numerical. I mean, even this, I mean, you could ask the same question for like much simpler, right? What are those two missing 5 p.m. coefficients that Stefano was talking about yesterday? Forget this spread. So even that is not feasible.
So basically, we have to wait for the self-force people to do online.
Yeah, or even eccentricity, let's say the circular orbits would give us some more equations. And as Fabian mentioned, there was a paper out about a month ago. It was the first one, and all the results. Spin and eccentricity, and that is some good input, and we need to see if those are even untrue.
And these other talks,
Right?
idea about it. We can start to think about after the results.
No, it's just
Okay. I don't want to cut things back, so questions, please.
Yeah, I have a question. Like, I mean, everyone from the radiation case, right? So it's not that radiation sources don't have a smooth energy limit, and there is the heat bound that was described in the 80s, like relating the scattering angle together with the rapidity. So that plays bound in the PM's function. So now when you spin, presumably there is a similar bound.
Yeah, it is very
sorry?
Yeah.
What's the bound? You know this?
No, I don't know the bound, but
okay.
But you expect something.
Yeah, because the spin and the radiation somehow come together. I mean, they both give progress in the high energy. It's very simple. I mean, somehow it's different spirits, but it's kind of problems, and it's expected that you should get a bound related to the spin as well. The validity and so it's for me it's very natural that it's broken, like what you said, because I think that the energy limit, not having a smooth energy limit implies that you should shift symmetry. Is that correctly? Or at least yes. Yeah. So
They're independent. It's just that the Teukolsky solution that we came up with have both of them. The breakthrough symmetry and
Yeah.
But there are choices for coefficients. Either or.
Yeah, but actually one implies the other.
No,
Yeah, I have shared. At least it's interesting. If you have a chip symmetric amplitude, you have a high finite energy.
Yeah, that's
But
what
the opposite is not true.
that's definitely not true in general. It might be.
Yeah. In general,
Like,
I mean,
that's steadily fifth.
well, that's what I'm saying. If you go up to spin to the six, you impose chip symmetry, even you have three coefficients, your scattering angle is well behaved in the high energy.
The shift symmetry alone does not fix all of it.
No, definitely not.
And within that,
But also,
in fact, that's what I would get it all saying. Is that shift symmetry alone doesn't fix a unique amplitude, but shift symmetry along with demanding the best possible behavior in the high energy.
oh yeah,
Meet those 32 as well.
Right.
Meet those 32 as well.
According to this one thing that we did, according to us guys, I don't know, maybe we have different opinions, but I'm much more skeptical than our analytic continuation. Something like that.
So you say the saving loophole, like either after analytic consideration is completely resolved.
Or different kind of solution, maybe. And also, you don't have to, it's worth mentioning where the other side, you don't have to do this. You can get the result for an actual black hole with the horizon with A less than GM. And we did that, and it's also in the paper. And nothing expanded.
Yeah.
And so that is also perhaps the most important result of like how to use that, how to interpret that as a different other there.
yeah.
These diagonal functions, nothing is so that's
Yeah, in principle, you're gonna have both.
that's right.
That's a more rational.
Yes.
Yeah, that basically resumming.
Size 0 is the derivative.
So size 0 is the diagonal function, yeah. Real R is just a
Yeah.
So yeah, in principle, you can match and extract a Compton, which is valid for A smaller than 1. It's just that this is not the full story. There are some pieces which we haven't matched. That's why.
See, so the generalization of the exponential is a diagonal.
No, it could be more than that. At speed to the 6, you get.
Realize this function is not just.
And there's also maybe these dynamic points don't really belong in that true level altogether. Which is what we're trying to describe. Maybe they really belong with contributions to
Well, still, you have to, I mean, for the perturbation theory to be sensible, you do have to get, there has to be some consistency with the results that are reported. And, but if you come and say, okay, minimal thing is okay.
Well, in general, it's polynomials. Well, basically, it's sure because, I mean, if you look at the MST solutions, these guys, so in general, you have these gamma functions in there, and you know the digamma, trigamma, and so on, and so forth, just combined from expanding these guys.
Sure.
So you will expect that you can resum everything into solvent gamma functions. But hard to write an answer, but that's okay.
Okay, that's the discussion.
So